Okay, so good morning again. And before we start today, the lecture of today, any questions from the previous week? Any question about project 3? No?
Generally, I think there's a part that is confusing on what exactly we should do in the functions, particularly with the time when we set the waiting time. It confuses me how a function should manage setting the waiting time for the method.
Okay, let's do like this. Hold your question for the break. We can discuss it in a break. Okay. Yeah, so, okay. So thankfully, we are done with the CPU scheduling. So I will update those slides. There is some issue in the outline is not correct. I will fix this and upload the slides again. But for now, I have uploaded them and you can follow them if you want. But we are now last couple of weeks, even like more than couple of weeks, we were talking about CPU scheduling. And what we were talking about was like, if we had the basic issue which we were discussing was this, like if we have multiple processes and we want to schedule them in a concurrent way, then how can we do this? Both on a single core processor and also on a multi-core processor. So what are the scheduling algorithm? What are the parameters, performance parameters, which we need to keep in mind while we are evaluating those scheduling algorithm? What is the different pros and cons of different algorithms and so on. So today we are going to talk about an issue related to the multiple processes running on the same machine, but in a case where those multiple processes, they cooperate with each other. So we call a process as a cooperative process if its execution is affected by the execution of other processes running on the system, and it can also affect the execution of the other processes running on the system. So this is basically happens when the multiple process, let's say two processes, to keep it simple. When two processes, they have some sharing data among them, data or code, right? For example, you remember like when we do the forking, when we create a new process. So what happens that the child process, it shares initially everything with the parent, including code and data. But if you, after forking, if you do the execute command in Linux, so what happens is that the whole address space of the child process is overwritten by a new program. And from that point onward, it doesn't share the code and data with the parent process. But if you don't do that, you do only forking, then the child and the parent, they share everything, right? So this is an example of where two processes, they are sharing something, which means possibly data or code, and they can affect the execution of each other. For example, if the child changes something in the data, then that change will be visible to the parent. And if parent uses that modified data, its result will also be changed. Another example we saw was in another slide where we talked about the producer-consumer problem, right? You remember it, right? Where we said that, okay, let's say we have a process which is producing some data, and then it is sending that data via a shared buffer to the consumer process, and the consumer is using that data, okay? So again, they are sharing the data, and basically here again, the producer can affect the execution of the consumer process, right? So we name these processes as cooperating processes. Now, when we have two or more cooperating processes, now what happens is that we can end up in an unwanted situation, where the result of execution is not deterministic. It is not deterministic basically because of the fact that the output of the result or output of the execution, it depends upon the order of the execution. If you remember, we have briefly touched this problem. So where like two processes are sharing the same data, but the order in which they access the data, it can affect the final output of the program, right? So we are going to discuss that how we can handle this kind of situation. So let me lead to the slide. I think I have covered most of it, but again, concurrent access to the shared data may result in data inconsistency. We have a more concrete example to explain this first sentence or first statement. So it will become clear what does it mean by data inconsistency resulting from shared data. So if you need to maintain data consistency, then we need some mechanism to ensure the orderly execution of cooperating processes. We need to ensure that no two processes, they access the same shared data at the same time, okay? So here is an example in the figure where three processes, they are trying to access the same shared data. And this shared data can be in any form, like it can be a shared memory variable, it can be a global variable in a multi-threaded program. We had an example earlier, right? So where if you have global variable and then you have multiple threads, then that global variable is visible or accessible by all the threads, and the changes made by any one of those threads is visible to all other threads, right? Another example of the shared data can be a file, like you have in the main thread, you have created a file or you have opened a file and then you have spawned the threads. Now all the threads which are spawned by the main thread, they will have the access to that file or a kernel variable, right? So all these are the example of the shared data. So we talked already about the producer-consumer problem, but if you remember, when we talked about the producer-consumer problem last time, let me see if we have the code for that older code here or not. No, we don't have. So if you remember it, what the algorithm or the code we wrote for that producer-consumer issue problem was, like, what we were doing is that every time before your producer puts the data in the buffer, we check the size of the buffer, right? So if it is like, let's say you have the buffer size with element of 5 elements. So if 4 elements are full, already 4 elements are produced and put in the buffer, then the producer is not going to produce a new element and put in the 5th slot. So one slot was always empty, right? And in the same way, consumer, it will, at most, it can consume 4 elements. So one slot was always empty, even from the perspective of the consumer. So which was basically the issue was that we were wasting one slot in the buffer. So now let's say what we do is that we improve our algorithm and we write it in a different way, where what we do is that between the producer and the consumer, not only the buffer is shared, but also we have another variable which is named as count. So basically what we are doing here is that, let's say how many, 1, 2, 3, 4, 5, 6. Let's say you have 6 elements, you can place 6 items in the buffer at a time, at max, right? So what you do is that you use the count to track the number of the elements in the buffer, currently in the buffer. So what does the producers do is that every time it produces a new element and you want to put it in the buffer, so what it does is that it increments the count, right? So after putting the element, and the consumer, what does it do is that after retrieving the element from the buffer, it decrements the count by 1, right? So count gives us counts gives us the number of like currently occupied slots or currently existing number of elements in the shared buffer. Okay, so in this way there is no empty slot, so we are not wasting the slot in the shared buffer because now we are maintaining that check using a different variable that is count, right? So this is how, if you try to write the code using this new approach, this is how the code will look like. How I am explaining this to bring up the issue of like, what is the issue when we have two cooperative processes and they have the shared data, then what issues we can end up with. So now if we look at this code, it is written in a slightly different way as compared to what we have seen in one of the earlier slides. So again, you have like an infinite loop on the producer side. It produces a new element. We don't know how it produces, and we don't care about it for now. So you first always check the value of the count, producer always check the value of count. If the value of the count is equal to the maximum size of the buffer, let's say it was 6. So if the count is equal to 6, you can't do anything, you must wait, right? Because it means buffer is full, the shared buffer is full, you can't put another element. But if it is not equal to buffer size, then what you do is that whatever next element you have produced, you put it in the buffer at this index in, which is maintained by the producer for the purpose of tracking where to put the next element, right? And then you increment the in variable or index, but then you also take the remainder by buffer size, so that it means that you always keep moving from 0, 1, 2, 3, 4, 5, again 0, 1, 2, 3, 4, 5, and so on, right? So it is like moving in circle. And then you increment the count to indicate that the total number of the existing items in the buffer is incremented by 1, right? So if you look from the producer perspective, this is how it should look like, or how it should work. Now, look at the consumer side. So basically, we are doing the similar thing with a slight difference. So now what you are doing is that you first check if the buffer is empty. So if the buffer is empty, there is nothing to retrieve, right? Nothing to consume. So what you do is that you are checking if count is equal to 0, so just keep waiting. But if it is not equal to 0, it means there is something in the buffer, so it is not empty. So what you do is that you take the you retrieve the element from the index out, and out is again you use it to track from where to get the next element in the buffer, and then you increment the out to you are just increasing the index to remember from where to retrieve the next element. The next time I get the chance to retrieve, and here you are decrementing the count so that you know that okay, now total number of elements in the, because you have retrieved 1, so total number of elements in the buffer they have reduced. Now, if you look at these two codes, remember that we are talking about cooperative processes. So they are, because they are sharing something with each other, and what they are sharing the memory buffer, and they are also sharing this count variable. Okay. So if you look at this code from independently, like if you independently look at the code of the producer, it looks like it will work fine, right? If you look at the code of the consumer, it looks like it will work fine. But if you look at them in a collective way, like both are running at the same time, do you think there will be any issues? Or do you think it will work correctly? There will be no issues. Okay, go ahead.
That's a really great counts each one and also the buffer.
Yeah, that's correct, because they are accessing the same count variables, and their whole execution is based basically on the like producer, before putting any element in the array, must first check the count. Similarly, consumer must first check the count variable before retrieving anything. So they are accessing the same variable, and they can end up in a race condition. What does it mean? So let me try to explain the same thing which he said, but in a more detailed way. So now assume that we are running the same example, and we are taking the snapshot. We are at a particular time point during the execution. Okay. Suppose that at that time point, there are 5 items in the buffer. Okay. And then the producer, assume that producer has just produced a new item, and it is it is at the time point where it is going to put that new item in the buffer. On the other side, the consumer is about to retrieve another element from the same shared memory buffer, which basically means, so if you go back into the code here, so basically what we are saying is that, so both are like, both have completed this statement, the producer has completed this statement, and the consumer has also completed this statement, and the next statement they are going to execute is, producer is going to execute count plus plus in like next cycle, let's say, and the consumer is going to execute count minus minus. Okay. Now let's see how we will end up in the race condition. And after explaining the problem, then I will tell you what the race condition basically is. Okay. So it means that though both they are going to execute count plus plus and count minus minus statement in their next cycle. So now there are two ways, like it is possible that producer, it first puts the data in the shared memory buffer and then this is followed by the consumer, which retrieves the data, or consumer first retrieves the data and then producer puts the data, the next element. Okay. So I mean, they can execute in any order. We have no control over their order of execution, right? Because it depends why they can execute in any order, because it depends which one is scheduled first, right? By the scheduler, right? Depending upon, let's say, on the scheduling algorithm. So now if we look deeply at a more lower level of how these count statements, increment and decrement statements are implemented. So if you want to increment a variable, so on the assembly level or more lower level, at hardware level, how it is implemented is that you have this count variable in the memory, you bring the value of that variable from the memory and put it in the register, let's say register 1. We are looking from the side of the producer now, first, count plus plus. And then you increment that value in the register. So register 1 is equal to register 1 plus 1. And then you put that incremented value back into the memory, that is the variable count, right? Now on the counts, on the decrement side, the same thing happens. So first let's say on the consumer side, you read the value of the variable from memory and put it in the register 2, decrement it by 1, the register 1, and then put the value of that register back into the memory count, right? Here we are assuming in this particular example that producer and consumer, they are using different register 1 and register 2, right? But it is also possible that they use the same register, because let's say if there is context switching and first the producer was running and there is a context switch, now what will happen, that the value of its register 1 will be saved in the memory, and then that same register 1 will be used by the consumer to decrement, right? But here, let's say we keep it simple and we say that they have their own, so they are using different registers, not the same register. So this is how, I mean, the same thing which I said in the previous slide. So how things are happening, a graphical animation of the same thing. So let's say initially we have the variable count equal to 5, which we said basically that we have 5 elements in the shared memory buffer, right? So now if the producer first executes this statement, so it means we are putting the value in the register 1, then we are incrementing that value, so it becomes 6, and then we put that value, we have to put that value back into the memory. But we cannot always guarantee that this will happen in the same sequence. Why? Because producer is a separate process, consumer is a separate process, and let's say once these two statements of the producer are executed, after that a context switch happens, which basically means the scheduler kicks out the producer and it allows the consumer to execute. And as a result, what happened that this statement of the register 2 is equal to count of the consumer is executed, not count is equal to register 1, register 1 of the producer. So it loads the value of the count from the memory, because in the memory, remember, the data is not yet updated by the producer in the memory. It has not executed count is equal to register 1. So in the memory, it still has the stale value, the old value. So what happens that register 2 gets the old value here, and then it decrements the value. So it becomes 4. And let's say after that, consumer is kicked out and producer is scheduled again. So now it is updated, the count is updated in memory, it becomes 6. And then after that, the count is equal to register 2 statement of consumer is executed, and as a result, we get the value of 4 in the memory, right? So is it correct? No. Why? Because we initially assumed that the value of the count was equal to 5. So if producer is incrementing it by 1, it should become 6. And then if consumer reduces it by 1, or decrement, it should become back to 5, right? So 5 is the correct value which we should expect, right? But we don't get it Why? Because before the producer completes its execution of count plus plus, it is interrupted in between. It is like kicked out in between. And as a result, what happened that consumer never sees the updated value of 6 in the memory. It still sees the old value of 5 and then decrements it. And then the order in which the memory data is written in the memory, it is also not like, there is no guarantee. It depends upon the scheduler. So what happens that first 6 is written and then 6 is overwritten by 4, right? So which means that our execution of the program will be incorrect. And this is known as race condition. Race condition is the situation where the output of the execution, it is different. Two things. Output of the execution is different for different runs. Maybe this time I'm getting the output of 4, or like memory value of 4. But maybe if I run it again, next time I will see 5 or maybe 6, right? It depends upon the order. So there are two things. One, the value of output is different for different runs, and this difference basically depends upon the order of execution. It is originating from the order of execution of the cooperating processes. So this is known as race condition. And this is problematic because it can possibly give us the wrong result. It can also give us correct result sometimes, because here the possible values can be 4, 5, and 6, right? So 5 is correct, but 4 and 6 are incorrect. So it can give us potentially wrong values, and it will be difficult to debug. If you have the wrong value, you can maybe next time you run and you don't see that wrong value, and you will be like, what's happening? Okay. So this is like the same listing of the order. I'm not going through it, which we have already seen in the previous animation. So initially we assumed that count is equal to 5, and we were expecting that the final result will again be 5 because one decrement, one increment, so it brings it back to 5, but we saw the wrong result of 4. Why? Because before the producer completes its operation, count plus plus, it gets interrupted, and the consumer gets the chance to run. Okay, so let me read the slide. I think I have explained everything, but still again. Count value, it may be 4, 5, or 6 in various runs, right? But it should be 5 as a result of one increment and one decrement. So these interleaved accesses to count cause data inconsistency. So 5 is like correct value, 4 and 6 are incorrect values, but they are also possible output values. Incorrect, but possible output values. So that our data, our result is inconsistent. So such problematic situations are called race conditions. And we should develop programs that do not have race conditions. And I told you why. Because one, they can end up in wrong results. Second, they are difficult to debug. So race conditions are harmful. They are not easily reproduce wrong results. Okay. How can we solve the problem? Yeah, lock is just a mechanism, but the approach basically is that we should, if we go back to this example here, we should not allow consumer to start execution until the producer is done with count plus plus, the all three assembly statements, right? And only then we should allow the consumer. Or similarly, if consumer is executing these three statements, we should not allow the producer until consumer has completed these three statements, and then allow the producer to execute this count plus plus, right? So lock is the one mechanism to achieve this target. So in previous example, for consistent result, either count plus plus should be executed and finished first, or count minus minus should be executed first and finished. There should be no interleaving. To avoid the race condition, we need to enforce non-interleaved accesses, that is atomic accesses to the shared data. Atomic accesses mean that these three things, register 1 is equal to count, where you are loading the data. So this is a load instruction, load operation. Then register 1 is equal to register 1 plus 1. This is modification or modify statement. You are modifying the data. And then count is equal to you are storing. So load, modify, or update, and then store. So all these three should be done in an atomic way, in a single step, unbreakable step. So either we should be able to do this, mean we should be able to achieve the atomicity, and if we are not, then we need to provide synchronization mechanisms where threads and processes, while they're accessing the shared data, they access the shared data only one at a time. Only one of them can access it at a time, right? Any questions? No? Okay. So now, how to handle the race conditions? Before answering that question, we need to understand another concept which is used in the context of handling the race condition, and that is critical section. So what is critical section? So the part of the program that is accessed and changing shared data is called, it's just like in our example, we have this producer and consumer, right? So we have what is shared between producer, process, and consumer, a shared memory buffer, and also a count variable. And they are not only accessing it, they are also updating and modifying it. Both are modifying the count variable, they both are also changing the content of the shared memory buffer, right? So which means that count plus the shared memory buffer makes the critical section in this particular example. So any part of any data which is accessed by multiple processes and also updated. Let's say one process is only accessing and the other is updating, still it makes the critical section. But let's say two processes are accessing the data, but only for the read purpose. None of them is modifying. It doesn't make the critical section. One of them should be at least updating it. Okay. So here is an example. Maybe the coloring scheme is not very good, but let's say you have three processes, 1, 2, and 3. And process 1 is modifying variable x and y, 2 is modifying x, y, and 3 is also modifying y. So I don't know whether you can see these boxes or not, but x is since it makes a critical section between process 1 and process 2. And not only x, y is also the critical section shared between three processes. So from the perspective of 1 and 2, only x is the critical section. But if you consider also process 3, so y also is the part of the critical section. Okay. So which basically means that if you don't have the process 3 in the situation, then the critical section composed of only x. But if you have process 3 also running, then the x and y both have the critical section. Any questions? Okay. So what we do here is we are just introducing some terminology. So we have talked about what is the critical section. We should allow only one of the cooperative processes to enter the critical section at any given time. There should be no more than one process executing that part of the code, which is accessing the shared data. Okay. Otherwise, we will end up in the race condition. The other part of the code, which is not shared, which is not critical, it is known as the remainder section of that process. So the remainder section is one. The remainder section of a process is one, which is not shared with any other process. And if let's say you have 10 processes and each one of them have their own remainder section, which means each one of them have some section which is not shared with anyone else, we want those remainder sections to be executed in parallel at the same time. So this is desirable. This is desired for the remainder section of each process to run in parallel, but we don't want them to enter in the critical section at the same time. Okay. So we want them to be serialized when accessing the critical section, but otherwise they can run in parallel. Okay. So let's say you have a process which has let's say which is running an infinite loop. It has some critical section and that it has the remainder section. So in order to avoid the race condition, what you need to do is that you need to first put some code before the critical section, which you are naming as the entry section, and some another piece of code after the critical section, but before the remainder, which we are naming as the exit section. The job of the entry section is to ensure that only one process can enter the critical. Basically, you are requesting the access or requesting the permission to enter the critical section. And once you are done with the critical section, you need to do some action so that other processes, they know that you have exited your critical section and they can now possibly enter the critical section. Okay. So what we require is that entry section should be written in such a way that it allows only one process to enter. If you have written the entry section in a not a correct way, then what will happen that you will expect it to allow only one process, but actually it can allow multiple processes to enter the critical section. And we have seen an example in one of the previous lecture slides. We still have an example, but I just wanted to mention it. Okay. So how can we solve this critical section problem? Okay, let me finish this slide and then we can take the break. So how can we solve this critical section problems? For that, the first thing is basically obvious, which we have already talked about, which is mutual exclusion, that only one of the cooperative processes should be allowed to enter the critical section at any given time. Second, there should be a guarantee that at least one of the processes is able to make progress in its execution. Which basically what we are saying here is that there should not be a deadlock, right? So we will have an example maybe somewhere later in the, actually we have complete chapter, I think, on deadlock. But just to give you an example, let's say you have a table and you have 4 persons, P1, or you can say 4 processes, P1, P2, and P3, and P4, and they are going to have their dinner. And for having dinner, each one of them needs a fork and a spoon, right? Each one of them needs a fork and a spoon, right? So you need 2 resources to do your dinner, right? But let's say P4 gets the spoon, person 3 gets the fork. Let's say spoon 1, fork 1, spoon 2, fork 2. Person 2 gets the spoon 2, and person 1 gets the fork 2, right? None of them can do their dinner, right? Because, and this is like deadlock situation, none of them can make the progress because every one of them have occupied partial resources, right? So as a result, no one can make progress. What is the solution? In that example, we cannot give them more spoons and forks. That is not the solution. Yes.
Maybe place in a rule that no one can, that every person that gets a spoon is supposed to have a fork and no one else can access it that way.
Yes, that is known as ordering the ordered access of the resources. This is one option. The second option is it's not covered in this chapter. I just wanted to open your minds. What can be the other option? Release your fork. Let the other person have it. And once the other person is done, then you can do your dinner. Okay. Okay. So for critical, when we are solving the critical section problem, actually, when we are writing the code and we want to solve the critical section problem, we need to enforce one thing, mutual exclusion. No 2 processes enter the critical section at the same time. And second, there is no deadlock. There is no situation like if 2 or 3 processes are cooperating with each other, there should not be a situation where none of them is able to make the progress. At least one of them should be able to make a progress, right? And third, bounded waiting. I'm not reading the statement, I'm just trying to explain it. So bounded waiting mean we should not be in a situation where where one process is always starving. Like for example, in this particular case, let's say we end up in a situation where let's say process P4, it releases its spoon, and person P4 releases its spoon, and person P1 now gets the spoon and it starts having a dinner. But its dinner continues, let's say, for 1 hour, and then as soon as it releases its fork, the person 2 gets the fork. And then as soon as person 2 releases the fork, person P1 is again hungry, and it again starts eating. So as a result, person P4 is never able to eat, right? So there is other processes are making progress, but process 4 or person 4 is now never able to eat. So we also don't want to end up in that situation. So there should be mutual exclusion. There should be a guarantee that there is no deadlock, and there should be guarantee that no one will be starving forever. Okay. Any questions? No, then let's have a 10-minute break. And in break, I'm going to address your question.
Well, I have two questions. The first one is
Let me first open the project statement so that it's clear also to me. Okay, now you can ask.
that we have the task of creating the simulate the functions like first come first served.
Stimulate the algorithms, yes.
We have the pair and swap and those functions, which are enough to simulate the scheduler. But then we are requested to use multi-processes. I don't know how the multi-process fits there, because the point of the scheduler is to have the control.
Multiple processes or multiple threads?
I sincerely don't remember well.
I think threads, right?
Yeah.
Okay, so now what is the question?
Isn't that defeating the idea of creating the scheduler?
Isn't it what? Sorry.
Against the idea of the scheduler if I take multi-thread?
Okay. So his question is that the project is supposed to be about scheduling, and during my whole lecture we were talking about in terms of processes when we were scheduling. But now when it comes to the project, you are saying you need to implement the scheduling algorithm for threads. So there is a contradiction, right? There is no contradiction because our focus is the scheduling algorithm. So you can use that algorithm to schedule thread, or you can use that algorithm to schedule processes. Doesn't matter, right? You can just consider a situation where you have single-threaded process. It is a process, but it is a single-threaded process. So if you have 4 processes, you have 4 threads actually, right? Or you can consider the situation where you have multi-threaded processes, right? But each one of, like, remember there is many to one mapping between the process thread, user process thread, and let's say there is many to one mapping. So from the kernel perspective, even if you have 4 processes and each one of them are multi-threaded, from kernel perspective, there are 4 threads, 4 kernel level threads, right? So the scheduling is done by the kernel. So kernel will be what will be doing, it will be scheduling those 4 threads. And in Linux, actually, so what happens is that threads and process in the Linux kernel, they are almost the same thing, treated as the same thing. Okay.
Yeah.
So there is no contradiction because you can use that scheduling algorithm to schedule threads or to schedule processes. You can just assume you have processes which are single threaded.
Okay, but if I run the arrays just one in parallel?
Ask it again.
Won't the processes just run in parallel if I use multi-thread?
Okay. Now it depends upon your machine. And most probably you have multi-core machine. I don't think any one of you have single core for laptop, single core desktop, right? So if you are running on a multi-core, then they can run in parallel. But they can run in parallel only if your scheduler allows them to run. If your schedule says that no, stay in the ready queue, I'm not putting you on the core. Even if there is the core available, then only one of them can run, right?
Mhm.
Do you get it right?
Yeah, so only one can run.
You want me to explain or you?
No, that part I get it. It's just my computer can run them in parallel.
Yeah, but in the project, we are using the scheduler, and scheduler is controlling which one will run next,
Okay.
and it allows one of them to run at any moment. So even you have the multi-core, but your scheduler is allowing only one of them to run.
Okay.
Any other question?
It was just about I don't remember the name of the function, but it's about setting the waiting time because it happens before we run the code.
Setting the waiting time or finding the?
Find the waiting time. I think.
Okay, so what is the question?
So we have to set find the waiting time before we use the scheduler. I think.
Referring to like the shortest job first,
You know,
Are you did you mean burst time instead of waiting time?
no, it's a waiting time.
So we cannot find the waiting time
Yeah,
in advance.
find the averages based on the previous running.
no, yeah, I don't know if I read it wrong, but I think we are requested to find the waiting time, the turnaround, and the completion time.
Yes.
But before the scheduling,
Before the scheduling.
I think it is requested before.
Maybe I haven't read it in complete detail. Anyone who agrees with his question that is the situation, he's saying that this project want us to find the waiting time, completion time, and turnaround time before scheduling.
Yeah, I think so.
I don't
But
think.
it's in the file.
I don't think so. If that is the case, then what's the point of implementing?
Yeah, that was my question.
I don't remember that wording in there.
Deliverable, fill in the to do for such scheduling algorithm dot say implement the parents correctly simulate scheduling using alternate print of waiting times, turnaround time, equation for each thread result for such.
I think the function the first come first serve. It says in the to do first assign the waiting time, then create and join the threads.
Are you talking about scheduling algorithm dot C file?
Yes.
Let me open it then. Which function can you name?
First come first serve.
Calculate, compare and swap, calculation sum, first come, you mean first come, first serve thread?
No, the next one.
Okay. Implement the first come, first served scheduling algorithm, assign waiting times based on the
Or maybe it's just the wording that confused me, but
based on the order of arrival. Create and join threads, calculate and print the scheduling results. Okay. Yeah, I think the TA will be in a better position to answer this. Okay. So ask the TA.
Okay.
But I agree with you that if without running, we are going to assign the waiting times, then maybe there is some issue with wording. Ask the TA.
Yeah, okay.
I'm not clear on that. Okay.
Well, it's not said, you have to assign. You only have the arrival time, and you cannot calculate it before you go in. Even in the, there's actually another function on, yeah, but it's like you see.
Yeah.
But you cannot calculate it, you know, because you haven't gone, you say that you've gone, but you don't know.
But you're assigning it based on this time, so you have an array that's already predefined, that already includes a waiting time, you're just sending it through this function, so you don't have to actually. It's already there.
Yeah, but you haven't gone the schedule, you don't know this, the, which moment you're gonna start, you don't know the waiting time. I mean, you can do that, but you won't know it. Even if you have.
Okay.
So that is the point of completion. But completion. The fact that you don't have the completion implies that you don't know the schedule. What do you mean? You can do it. You can do it. Simulate the schedule, get the site, and then actually involve well, just make them. Yeah.
Or your first come first serve algorithm or all of this?
I didn't check first one, but I must have been on the description. You can check you can also see, you have not run the algorithm.
And the arrival time.
Okay, so okay, let's get back to the lecture. There is my slide. Okay, so we were talking about that if we are writing the code to solve the critical section problem, what are the guarantees we need to have for that code, right? And the next slide explains that, okay, what are the situations, just some examples of the situations where this critical section problem can arise. One is like the first case is we already have covered, that you have a multi-process application, which is, let's say, sharing a file, or it's sharing a memory segment, and then it can potentially face the critical section problem. Other is again multi-threaded application. So these are two different cases. Multi-threaded application where the threads are sharing the global variables, and again they can end up in the race condition if we are not addressing the critical section problem. And also the kernel code itself of a OS, it can also end up in the critical section problem. There is an example in the book. I haven't included in the slide, but I can explain it here. So of like one example of this situation where kernel can face the critical section problem. Let's say, you remember we talked about fork, right? So when we execute the fork, what we are actually creating a new child process. And when we execute the fork, the new process which is created is assigned a process ID, and that process ID is returned to the parent, right? So let's say if you have two different processes, you have process A and you have process B, and both of them are doing fork, right? So both of them will trap into the, let's say, here we have kernel. Both of them will trap into the kernel, right? So then kernel will handle the fork on the behalf of process A and the process B. And let's say when the kernel is done with the execution of the fork, it needs to return the process ID of the newly created process. So the newly created process for the process A will, because they are doing independently two different forks, so two processes will be created, right? Now let's say, we are not going to the detail of that, but let's say that the kernel uses some algorithm to assign the process ID to the newly created process. Let's say it has a list of next available process ID. And now let's say the next available process ID, next available PID is something, let's say 10. And let's say now, since the both forks are executed by the processor at the same time, so this PID 10 should it be returned to the process A, or should it be returned to the process B, or it should be returned to both of them, because this is the next available process ID. So if we are not placing any ordering on the fork, if we allow the two forks to be executed in the parallel, maybe they grab the next available process ID at the same time, and it is returned, 10 is returned to both of them, which will not be correct. Because if you are creating two different processes, they must have unique process IDs. Okay, so here the example is that next process ID is a shared variable which can create the race condition. Okay. So how can we have already actually seen that how we can solve this problem, but we have talked in very abstract ways, like we need to implement them, achieve the mutual exclusion. We need to ensure that there is a progress, at least for one of them, involved processes, and there is no starvation, right? And one way, there are multiple algorithms to achieve that, all three requirements. And one of that algorithm is Peterson's algorithm. So in this algorithm, by the way, we cannot use this algorithm on modern architectures or modern processors. Why? We will talk about it later. But let's first talk about the algorithm itself, and then why we cannot use. But then if we cannot use it, then why we are even discussing it, just to show that how we can achieve those three requirements. Okay. So let's say we have two processes. So you can use this solution only with 2 processes. Maybe you can extend it for multiple processes, but we are considering only 2 processes here. So, and among those 2 processes, we need to achieve mutual exclusion, progress, and what is third? No starvation. Okay. So we are assuming here that the load and store instructions, they are atomic. That is, they cannot be interrupted. Remember in the previous, when we say count is count plus plus. So when we break it, the count when we go down to the assembly level, it has 3 separate instructions, right? Load, update, and store back. So that is not atomic. We are assuming that we have atomic load and store. No one can interrupt between load and store. So the 2 processes, they share 2 variables in this example, in this algorithm. And those variables are turn and an array which has only 2 elements. And the array is named as flag. So turn, basically, it is if the value of turn is equal to 0, it's mean that it is the turn of the process 0 to execute. And if turn is equal to 1, it's mean that it is the turn of the process 1 to execute, to enter in the critical section. Okay. And flag, actually, it means it tells that whether a process is ready to execute or not. So if flag, the 0 element at the index 0 is equal to 1, then it's mean that the process 0 is ready to run or ready to enter, but it has not yet entered. Okay. And if flag is equal 1 is equal to 0, 1 is equal to 1, it's mean that the process P1 is also ready to run. Okay. Let me just read it. The variable turn indicates whose turn it is to enter the critical section, and the flag array is used to indicate if a process is ready to enter the critical section. So if flag I is equal to true, it implies that the process Pi wants to enter the critical section. It is ready to enter the critical section, but it hasn't yet. So the algorithm for the Peterson algorithm, it looks like this. So first you have critical section, you have remainder section, and as we said, we have to insert the entry section here and the exit section in between, right? So how the Peterson algorithm, how it implements the entry section, it implements the entry section by using these shared variables. Flag I is equal to true. So let's say if it is process I, so what process I, so depending upon the index of process I, let's say that it is 0. So it will set flag 0 is equal to true, and it will set 10 equal to j, not itself, j here. So you are saying 10 is equal to 1, right? In this example. So if I is equal to 0, j is equal to 1. So here the process I will set 10 equal to 1, but will set flag 0 is equal to true. And it can enter the critical section only if flag of j is true and 10 is equal to j. So basically what you are saying is that if you can enter the critical section if one of these 2 is false. Either first part of this AND condition is false or the second part of this AND condition is false, right? If any one of them is false or both of them are false, then the process I can enter the critical section. Otherwise, it cannot. So here what you are saying is that if the process J is not ready, or if it is not the turn of the process J, then I can enter the critical section, right? Similarly, if you look from the perspective of the process J, so what the process J will do, it will set flag J is equal to true and turn is equal to I, and it will check if the flag I is not true, which means the process I is not ready, or if the turn is not equal to I, then I can enter. And in the exit section, you just need to set your flag false. So to indicate that I am done with the critical section, I am now not ready to enter the critical section. So if you look at the code of the both side by side, so let's say we have process I and process J. And for ease of our reference, we are saying that let's say process I is actually process 0 and process J is process 1. So then this is how your code will look like. So here basically in the process 0, what you will do is flag 0 is equal to 2 and turn is equal to 1. And in the while condition, you are checking if flag 1, if the process 1 is ready and turn is equal to J. If both is equal to 1, if both these conditions are true, then I must wait. If one of them is false, then at least one of them is false, then I can enter the critical section. And same for the process 1. Okay. I give you like 30 seconds to look at the code of process I. J, so that you can understand. Okay, now here is the question. How many of you think that this code ensures the mutual exclusion? If you think that it ensures the mutual exclusion, raise your hand. One.
We're assuming that load and stores are atomic.
Yeah. 2% think that it will ensure the critical insight. Others, do you think the mutual exclusion will not be achieved, or you are like, you cannot decide? Who think the mutual exclusion will not be achieved? Okay, so it's mean everyone is like, and other people cannot decide. Okay, so you said that it will achieve the mutual exclusion. How?
Looks like it has a proper entry and exit section.
Yeah, but can you like try to walk me through the process which achieves the mutual exclusion? I'm not sure. Okay. So, okay, here is it how it works. We assume that load and store is atomic, right? Which basically mean if I am writing some data, let's say I am writing some value in the variable A, you cannot interrupt me until I have written the data. Then only after I am done, then you can update that data, right? Which means that store is atomic. In the same way, if I'm loading the data, until I get the data in my register, you cannot in between interrupt me and do something with that data, right? So now if you look at this code, so the process 0 is setting turn equal to 1. I'm talking in terms of process 0 and 1, not in ing. So process 0 is setting turn equal to 1. Process 1 is setting turn equal to 0, right? Since we said that store instruction is atomic, which means that when process 0 is setting turn equal to 1, it cannot be interrupted by process 1. And when process 1 is setting turn equal to 0, process 0 cannot interrupt it, right? Which means that we will eventually get only one final value. Turn will be either 0 or turn will be either 1 at any given time, right? So if let's say now execute this while statement from the perspective of process 0, if turn is equal to 0, then it will be waiting. Because if process 1 was the final one to update the turn, then the turn will be equal to 0, right? Right? So if let's say it updated the turn and then it was kicked out by the scheduler, and this gets the chance to run. And the next statement it has to run is this file statement. So it checks the value of turn. The value of the turn is equal to 0, which is not equal to 1. So this condition is false. So the loop breaks and it enters the critical section, right? Now let's say when it is critical section, in the critical section, it is kicked out by the scheduler. And this one is allowed to execute. Now when it executes the while statement, turn is equal to 0. So it cannot, and turn is equal to, so this statement is, this second part is true. And let's say the flag I is also true. So it cannot enter the critical section. Okay. So until it can enter the critical section only once the process 0 completes its critical section and sets flag I equal to false, then it can enter into the critical section, right? So in this way, we achieve the mutual exclusion. Any question? Or confusion? Okay. Yeah.
You mentioned that this method is not used in modern day systems. How come it really achieves mutual exclusion?
How come what?
How come it's not used in the modern system? It already achieves mutual exclusion.
Yeah, okay. So that is a good question, but the reason why it is not used in the modern system is like, let me try to, this next set of slide will answer the question maybe in a better way if I don't use them slides. So the basic reason is that in the modern systems, the compilers, in order to achieve the performance, let me not confuse you. The compilers, in order to achieve the performance efficiency, better performance, what they do is that whenever possible, they reorder the instructions of a process. Okay, so when you do the reordering, it can change the things. It can change the order in which the data is updated. And as a result, this program or this mechanism of achieving the mutual exclusion will not work because of that reordering. Okay. So here is like how we can explain the things. Let's say we first talk about another example, and then we'll come back to that Peterson, like why it doesn't work in the modern system. So let's say you have two threads. So and they share the data. The data which is shared is a flag variable of type Boolean, and its value is, let's say, equal to initially false, set equal to false, and an integer variable x, whose value is initially set equal to 0. Now the job of thread 1 is that it first checks the value of the flag. If the flag is not true, then it keeps waiting. So basically, if flag is equal to false, it will keep waiting. And if its flag is true, then it will print the x, right? And the thread 2, what it does is that it sets x equal to 100, and then it sets the flag equal to true, right? So what is the expected output if we run this code? There are two threads. They have shared global variables, flag and x, but the code they execute is different. So what will be the output of this code? How 0?
Oh, wait, no. So if it's false, it'll enter the
Any other answer? 100. So the output will be 100, but only if we assume that the instructions, the load and store instructions, they are not reordered. If they are reordered by the compiler to achieve the performance and increase the performance, then the result will not be 100. Okay, and here is how it looks like. So variable flag and x, they are independent of. So actually, what does the compiler do? That whenever you see that there are two variables which are independent of each other, and if the compiler thinks that if I reorder those accesses to those variables and I can increase the performance, it will reorder them, right? So here flag and x, they are both independent. So there is independent in the sense that the value produced by flag is not used by x. The execution of the print x is definitely dependent upon the while flag is not true, right? But the value of the flag variable is not used. We are not saying that print x equal to x plus flag, right? There is no dependency, data dependency, right, between flag and x. So if there is no data dependency between flag and x, load and store instructions, I don't know whether you are aware of data dependencies or not. Are you aware of data type of dependencies between instructions? So one dependency is data dependency, where what happens is this, like, let's say I have A is equal to 2, B is equal to A plus C, right? So if this is my program, I cannot execute B before A. Why? Because I must execute A before, because the output of the B is dependent upon the value, input or value of A. So here it is making the input, right? So this is data dependency. So I cannot reorder them. If I reorder them, I will end up in the wrong result, right? But if I have another program where I say A is equal to 2 and B is equal to X plus Y, there is no dependency between these two statements. And now if compiler thinks that if I execute B before this statement, second statement, before first statement, and I can get the better performance, it will reorder it. And this is the situation here. There is no data dependency between X and Y and flag, right? So if there is no data dependency, it will now possibly reorder. So the instruction flag is equal to true and X is equal to 100. Let's say that when the compiler compiles the code of the thread 2, it reorders these two statements. So if this occurs, then output may be 0. So in the original code, see, we are first setting X equal to 100 and then setting flag equal to true. There is no dependency. But if you first set the flag equal to true and then X is equal to 100, then what will happen? The thread one, it will see that, okay, flag is equal to true. So the while flag is, the statement will become false. So the control will fall through and it will print the X. And the X is not yet updated, let's say, and then it will print 0. Okay. So which is not what we want. So as what we have seen here is that as a result of the reordering, your program can end up in a wrong computation or wrong results. So same is the situation now here in the Peterson algorithm. So, okay, I cannot write, I don't want to rush through it, this slide. So let's stop here. In the next lecture, I can quickly give the recap of this thing, reordering, and then we can discuss this slide. Okay.